Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So within this module, we're trying to understand that how does the operating system manage the CPU, right? By providing this abstraction of a process. And within the second module, we are currently on the fifth topic, that is time sharing. So currently in this topic, we are talking about time sharing. And as you know, this time sharing is a concept where using which the operating system shares the CPU time among multiple processes, right? Which allows the users, we as end users, to run more number of programs on a limited number of CPUs. So this we have already understood what is time sharing, right? And we have seen that this time sharing is implemented via this technique known as CPU scheduling, right? So CPU scheduling is a resource allocation technique where the operating system is basically allocating the CPU among multiple processes. So we are trying to understand that how we are trying to understand CPU scheduling, right? And there are different questions that we are trying to answer about CPU scheduling. So in the previous few videos, we have been talking about the how question, that is how exactly is the CPU scheduling implemented, like what is the mechanism. So we saw all the different techniques and mechanisms using which CPU scheduling is done on a computer system, right? So now let us shift to the next question, that is when. So the question that we will try to answer in this video is that when can the operating system schedule the CPU, right? So what are the different times at which the operating system can or should schedule the CPU? So that is what we are going to discuss in this video. So without further ado, let's get started. So let us start the discussion with this slide. So as you can see, we are trying to answer, basically we are trying to understand CPU scheduling. And to understand the CPU scheduling, we are trying to answer several questions about it, right? We are trying to understand different aspects about it. So in the previous video, we have talked about why and how, right? That is, we have understood why are we doing this and how are we doing this. So now in this video, let us talk about when can we do CPU scheduling. So basically the operating system which is responsible for doing this allocation of CPU. So when can it do all of these things? So let us understand this. So this is the diagram that we have seen in the previous videos also. So as you can see, this is the CPU scheduling diagram, right? We have a hypothetical computer system which has a single CPU, and there are three processes that the operating system is trying to schedule on the CPU, right? So this is the time sharing. As you can see, the CPU time is being shared by all of these three different processes, right? So now in order to so now the operating system has a like it has to do CPU scheduling, right? So it has to first of all decide when at all can it do this. So if you see this diagram, right? So first process P1 is running, and then the operating system decides to halt, or you can say pause process P1 at some instant, right? And then switch to some other process which is P2, right? So what I'm trying to the question that I'm trying to raise here is that how does the operating system decide that this is a good point to stop process P1? How, why is this stopping at this point and not before this or later? Why can the process P1 not run for longer? Or why has the operating system allowed the process P1 to run for this much, right? Why not stop earlier? So question is, why not stop this process earlier? Or the other part is, why not let this process run for a longer time? So think from the perspective of the operating system. So when it decides to stop a process, what is the right time to stop the process, right? So this is the question that we should first understand, that what is a good time to halt a process and make a context switch. So let us try to answer this question, right? So the question that we'll try to answer is that when can CPU scheduling happen? So in order to answer this question, that what is a good time to schedule the CPU, let us first revisit this process state diagram, right? The answer to this question is kind of related with this process state diagram. So we have talked about the process state diagram in the earlier videos also. So what is this? It is basically a diagram that depicts the life cycle of a process. That is, it conveys what are the different states that a process can be in during its lifetime, right? So I will quickly review this diagram, right? So when a process is created, it is in the new state, right? And from new it goes to ready state. So in the ready state, this process is basically ready to execute instructions. Here it is ready for the computation. So here basically it is also waiting for the CPU to be assigned. In the ready state, it does not have the CPU. So eventually the operating system will pick that process and schedule it on the CPU. When that happens, it transitions to the running state. In the running state, the process has the control of the CPU and it is executing its instruction. That is, it is doing its work. So this is the running state. From running state, it has three options. First, the simple option is that it can finish its instructions, right? All of the instructions that the process had, let's say that gets finished, then the process will transition to the terminated state. In this state, basically the process has finished its work and all of its resources will be deallocated. The process will be terminated, right? This is the simple case. The other cases are that the process can either go to the waiting state or the ready state. So let's first talk about this one. So it could happen that the process was executing instructions and now suddenly it has to wait for some event to happen before it can continue further execution, right? So there could be several reasons why this could happen, right? The process needs to wait, for example, whenever it needs a resource. Let's say that resource is not available, then the process has to wait for that resource to be acquired before it can continue further execution. Or let's say it initiated a I operation, it is requiring to read some data from, let's say, a hard disk. So unless that data is available, unless that data is read from the hard disk, that data cannot be processed. So further processing depends on that data to be available. So the process needs to wait for that IO operation to complete. So waiting for IO operation is one of the major reasons why a process has to wait. Other reasons could be that the process is waiting for its child process to terminate. Many other reasons exist, right? So the process can transition from running to waiting state. And finally, when that event happens for which the process was waiting, it transitions back to the ready state. And from here, it can again be allocated the CPU and it can go to running state. So this is one type of cycle: running, waiting, ready. The other type of cycle, as you can see, is running and ready. Here also the process can cycle. Let's say the process was executing instructions on the CPU, and we know that it won't be allowed to execute for like as much time as it wants. There is a certain limit to how much time it can spend executing instructions on the CPU. So we talked about timer interrupts, right? If the process has spent some considerable amount of time, then it will get interrupted by the timer interrupt and the control of the CPU will be taken away from the process. Even when it is ready to execute, it will be like the control, it will be preempted, right? The control of the CPU will be taken away from the process and it will go back to ready state. And later on, it can again be given the control of the CPU. So this is one another cycle, that is running and ready, right? So this is how a process spends its lifetime, right? So now let's come back to the question that we had raised, like what is a good time to schedule the CPU, right? So if you see this diagram, when the process is running, then we have a open question, right? When the process is running on the CPU, the operating system has an open question that is this a good point to stop, or should we allow the process to run for some more time? There are only two options: either we can let the process run or we can pause the process. So this question is only valid if we are in the running state, right? But if the process transitions to the terminated state, right, if the process gets terminated itself, then there is no open question. Now the process has terminated, it has halted on its own. Now the operating system definitely has to do CPU scheduling, right? You understand what I'm trying to say here? Basically, let me explain this via a diagram. Let's say we have a process A, right, and it requests termination from the operating system, let's say via a exit system call, right? It could also be the case that it is getting terminated forcefully. Whatever be the case, when the process is getting terminated, now we do not have that open question that whether to let the process run or to like halt the process. The process has halted on its own, right? So in this case, we definitely have to perform CPU scheduling and give the control of the CPU to some other process, right? So when the current process terminates, the CPU needs to be scheduled to a different process. So definitely this is one of the cases that if a process terminates on its own, then we definitely have to do CPU scheduling. So this is one of the opportunities to do CPU scheduling. Let's talk about some other cases. Similarly, if a process goes to waiting state, right? The common thing between waiting state and terminated state is that in both of these states, the process can no longer run. I mean, even if you give the control of the CPU to the process, it cannot execute. First of all, in the terminated state, it is obvious that it got terminated. It has no more instructions to execute. Even if you give the control of the CPU, it does not have any instructions left, right? Whereas in the case of waiting state, although it has more instructions left to execute, currently it cannot execute because the logic says that for further execution something is required. It could be some resource, it could be some data, whatever is the case. For whatever reason the process is waiting, even if you can give the control of the CPU to the process, it cannot continue further execution. So here also there is no open question, right? As the question was there in the running state that whether to allow the process to execute further or not. In the waiting state there is no such question. The only option that the operating system has, that it has to halt the process and give the control of the CPU to some other ready process, right? To some better process who can actually execute instructions. So the second case we can see is that when the current process blocks due to whatever reason, the CPU definitely needs to be scheduled to a different process. So you can see again the process might block whenever it makes some system call, let's say for some resource or to do some kind of IO operation. We have talked about the wait system call, right? The wait system call allows the process to wait for its child process. So there are different mechanisms or different reasons why a process would go to wait, how it would go to wait. But whatever is the reason, whenever there is waiting, the process blocks. And when it blocks, even if you give the control of the CPU to the process, it cannot execute instructions. So it is a better thing. It's the only option, right? For an efficient computer system, it is the only option left that we give the control of the CPU to some better candidate who is in the ready state and has instructions left to execute, right? So both of these cases, terminated and waiting state, here we are not left with any option but to give the control of the CPU to some other process. We have to do CPU scheduling, right? The third case, let's come to the third case, when the process goes from running to ready state for a while, right? So in the ready state, the process is ready to execute instructions. If you give the control of the CPU to the process, it will definitely continue its execution. There is nothing stopping the process from continuing execution. It has instructions left and there is no logic to wait. It is definitely ready. If you give the control, it will execute. Right now, there is a question. Here, there is a question. Should we give the control of the CPU to the process or not? Let's see with this example. So when does a process go from running to ready state? It can go whenever it is interrupted, right? When the current process gets interrupted, the process which was executing on the CPU, right? It goes from running back to ready state. And this interruption can be due to any kind of device interrupt, not just timer interrupts. Any kind of device interrupt can put a process from running to ready state, right? So when the current process gets interrupted, the operating system can perform CPU scheduling, right? Now here is a question, to context switch or not. So you can see process A was executing instructions. It got interrupted due to some kind of device interrupt. You can see this is the device and the device interrupted the CPU. When that happens, the control of the CPU is immediately transferred to the operating system. Whenever there is a device interrupt, the code flow execution goes instantly from the user process to the operating system, right? The process A was interrupted. When there is an interrupt, the operating system will first of all deal with the interrupt. Whatever was the reason for this interrupt, it will service this interrupt. Let's say the device had some IO operation initiated earlier and now that operation has completed. So the operating system will deal with the device interrupt, right? Once the device interrupt has been serviced, now there is a open question. Shall we give the control of the CPU back to this process A? That is, should we resume the process which was executing earlier, or should we give the control of the CPU to some other process? Here we have a choice and we'll see this choice is important, right? But the point is that definitely when a process gets interrupted, this is a point when the CPU scheduling can happen, right? So we were talking about when all can we do CPU scheduling. This is definitely one of the times when when the operating system can perform CPU scheduling, right? And one last case is that when the process makes a system call, then also the operating system can perform CPU scheduling. So let's say the process A had requested some services from the operating system. Let's say it is trying to allocate more memory, right? So the control will go back to the operating system. The operating system will allocate more memory to the process, but it is not necessary that the control be given back to the same process. It can be given to some other process also. Obviously, when this process A gets to execute later on, it will do something with the memory. But the operating system here has just fulfilled that request, whatever request this process was making. Here the operating system has just fulfilled that request by executing the system call, but it is not always necessary to give back the control to this process. After doing memory allocation, the operating system can very well give the control of the CPU to some other high priority process, right? That can also be the case. So if you see what is common, whenever the control is going to the operating system can do CPU scheduling. In some cases, it has a choice. For example, when the process is interrupted or when the process has just invoked system call, it has a choice that should we switch to some other process or not. Whereas in some cases, we do not have a choice. The process got terminated or it got blocked. The operating system definitely has to switch to some other process, right? So let me summarize. When to do CPU scheduling? There are several opportunities when the control of the CPU goes to the operating system. We talked about these cases. Either the process can get terminated or it can block itself due to some kind of waiting. It could get interrupted due to any kind of device interrupt. It could be a timer interrupt also. And finally, the process could request the operating system for some services. Then also the control of the CPU goes to the operating system. So now let us make a distinction. There are two cases. In first two cases, the process cannot be executed further. Even if you give the control of the CPU to the process, it cannot execute further. We talked about this, right? In case of termination, there are no more instructions left to execute. In case of waiting, the logic of the process is such that even if you give the control, further execution cannot happen. Something has to happen for which the process is waiting. Unless that event happens, the further logic will not proceed. So in these two cases, the process cannot be executed further. But in the latter two cases, which is the process either got interrupted or it invoked a system call. In these two cases, process can definitely be executed further. It is not blocked, it is not terminated, it has instructions left to execute. It is just the case that here the process got interrupted, right? It got interrupted. And in this case, it has requested some service. And when that service is fulfilled, it can execute, right? So there are two cases, right? So depending on these two cases, there are two types of scheduling. If the operating system only does CPU scheduling when the process cannot be executed further, then that kind of scheduling is called non-preemptive scheduling. Or the other case is that if the operating system can do CPU scheduling in any case, right, then even if basically if the operating system can schedule the CPU, basically I mean to say do a context switch, even if the current process can be executed further, this is called preemptive scheduling, right? So understand the difference. All of these cases have one thing in common, that like there is an option with the CPU that it can context switch to some other process. In the first two cases, the operating system does not have the other option, that it has to make the context switch. And if the operating system only context switches to some other process in these cases, then such an operating system or such a scheduling policy is called non-preemptive scheduling. Here basically we are not taking the control of the CPU from the process forcefully, right? The process itself has given up the control of the CPU due to termination or blocking, and that is why we are giving the control of the CPU to some other process which is ready to execute, right? Here basically the scheduling is kind of nice, you can say, but here we are being nice to the processes. We are allowing the processes to run as much as they want, right? And only when they get terminated or they block, then only we are giving the control of the CPU to the to some other process. Here we are very cooperative with the process. Here we means operating system. But in the other two cases, the operating system is not so nice to the processes. Even if the processes want to execute further, the operating system does its own thing, and depending on the scheduling policy, depending on the constraints of the system, it takes the decision whether to continue execution or not. Even when the processes are ready and can execute, if you give the control of the CPU to the process, here in the second case, it depends on the operating system. It can also give the control back, or it can do a context switch. So in the second case, here this is called as preemptive scheduling. Even when the processes are ready to execute further, the control of the CPU can be kind of taken away from them forcefully and given to some other process, right? So these are two different, so these are all the different cases when the operating system can do scheduling, and depending on whether the scheduling was done in a case where the process could no longer execute further, it will be called non-preemptive. Otherwise, if the scheduling was done in a case when process could have executed further, this is important, the process could have executed further but still it was context switched, then those such a scheduling policy is called preemptive scheduling. So now let us discuss the differences between non-preemptive scheduling and preemptive scheduling in detail. So let us discuss the differences between non-preemptive scheduling and preemptive scheduling in more detail. We'll see some more points. So this point, first point we already talked about, right? In these two policies, there is a basic difference in that when does scheduling occur, right? In the first case, scheduling happens only when the current process can no longer be executed any further, right? We saw these two cases, that is termination and waiting. Whereas in the case of preemptive scheduling, scheduling can happen whenever control is transferred to the operating system, right? In preemptive scheduling, whichever is the case, it could be like in all of these four cases. If there is a case, if we are doing the scheduling in all of these four cases, right, which includes the cases when the process could have executed further, right? These two cases to let's not talk about, because these two cases we do not have a choice. But if we consider all of the cases, and if we are also doing scheduling in the cases when the current process could have executed more, then that case is that is a preemptive scheduling, right? So this is the basic difference. Now let's talk about the execution duration. So here the process can technically execute indefinitely. So here the operating system is not putting any constraint on the process which is currently executing. So if it is the case that the process falls in an infinite loop, then the operating system will never stop that process. So technically the process can execute indefinitely, right? Whereas in the case of preemptive scheduling, the process is allowed to run only for a fixed interval of time at maximum. So when I say at maximum, so here let's say the current process, right, it is not terminating, it is not blocking, and it is not also getting interrupted, right? All of these three, if they are not happening, also the process is not making system call, then finally if the process is not giving up the control of the CPU in any way, then finally we do have a timer interrupt, right? The timer interrupt is always there. Even if there are no other device interrupts, we have an explicit timer interrupt which guarantees that after a certain period of time, after a certain interval, the timer interrupt will go off and the process will definitely get interrupted. So that is the maximum duration, that is the interval of the timer interrupt for which a process gets to execute on such a when the operating system is following such a policy, right? So here, right, the basic difference between the two is that in the first case, there is no constraint on the time. In the second case, let's say there is a case when the process is not giving up the control in any way, it is not getting interrupted, it is not blocking, it is not terminating, no system call. In that case also, there is a timer interrupt, and it can only allow execution for a fixed interval of time at max, right? Before that also the process can be like the control of the CPU can be taken away, obviously, if any other event happens, right? We discussed. So this was about the execution duration. The next point is that the requirement of timer interrupt. In the first case, there is no requirement of timer interrupt because we are allowing the current process to execute as much as it wants to. Only when it will terminate or it will block, when it gives up the control of the CPU on its own, then only we are pausing that process. Otherwise, we are not. So no timer interrupt is required. So there is no requirement for a timer because there is no constraint. We are allowing it to execute indefinitely, right? In the second case, a timer interrupt is a must, right? So in the absence of system calls, if the process is not making system call, it is not terminating, it is not waiting, right, it is not blocking, and if there are, let's just assume there are no other device interrupts, then how do we stop the process? We must have a way to stop the process after a fixed interval of time. So in preemptive scheduling, we have a timer interrupt which is a must, right? So if none of the things are happening, then after a fixed interval of time, the timer will definitely go off. So preemptive scheduling requires a timer interrupt. The last difference between non-preemptive and preemptive scheduling is the use case. So the first approach was used in early batch computers, right? Early batch computers use these non-preemptive scheduling techniques, whereas all modern computers rely on preemptive scheduling. So let us understand this point. So basically, in all of the modern computers, we have multiple programs that we want to execute on a limited number of CPUs. That is why we are doing time sharing, right? And also in modern computing, response time is also important, right? All of these processes should be given the control of the CPU. If we are not responsive to all of the process, that is something that we do not want. We as users are interacting with several processes, right? And if only one process executes, the other processes that we are interacting with will be unresponsive. That is a user experience that is we do not want to provide such a unresponsive user experience, right? So time sharing and frequent switching, right? All of these are required in a modern environment where users are launching several programs, interacting with them. So not just foreground processes, there are several background processes also that need to be executed. So time sharing has to happen. We have to frequently switch the control of the CPU among different processes, right? So for frequent switching, timer interrupt is a must. We cannot let a process run and wait for it to terminate or block. We cannot rely on the process to give up the control of the CPU. So all modern computers come with a timer interrupt, which allows the operating system to switch the control of the CPU among different processes, even if the current process does not give up the control of the CPU. So this was about modern computers. Earlier, this was not the case. People did not sit in front of the computer as we do today, right? Those were not personal computers. Those were batch computers where jobs were processed in a batch, right? In those cases, it was fine to let a process run till it wants, because no user is sitting in front of the terminal. So in batch processing, response time was not important. So a given process, if it wants to execute for hours, then it can. So earlier this used to happen, right? That non-preemptive scheduling was followed. The control of the CPU was given to the process, and only when the process voluntarily gave up the control of the CPU, then only the where there was a context switching, right? So that was earlier. Now that is definitely not the case. We want systems where multiple processes can execute together via this concept of time sharing. So here we need a way to have basically here timer interrupts are must, and processes here, even if the current process is ready to execute, right? The basic idea behind preemptive scheduling is that even if the current process is ready to execute and has more instructions to execute left, even then we will give up the control of the CPU will be taken away from it and given to some other process, so that all of the processes are given a fair share of the CPU. All of the processes have a good response time. So this technique of time sharing, in this technique of time sharing, a preemptive scheduling algorithm is a must, right? So guys, this was about this video. In this video, we basically talked about the question that when should the or when can the operating system do CPU scheduling. So we talked about the different cases when the operating system can do CPU scheduling. There are some cases like termination and waiting where the operating system does not even have a choice. It has to do scheduling. Whereas in other cases, when there are like interrupts, when a process gets interrupted or the process makes system calls, then the operating system can choose to switch to some other process, or it can allow the process to run further. So these are the different cases when the operating system can take scheduling decisions. And we also made a distinction between these two cases. If we are doing scheduling only in the first two cases, that is in cases when the process can no longer execute further, that is called a non-preemptive scheduling approach. Whereas if we are doing scheduling in all of the cases, and to be specific, we are doing scheduling even if the process can execute further, that is known as a preemptive scheduling approach, right? So this was about the different scenarios in which the operating system can choose to do CPU scheduling. So guys, this was it for this video. Thank you very much for watching. I will see you in the next video. Thank you.